So problem 2 in exam 2 is from chapter 24. We were talking about wavelengths, or when we were talking, not wavelengths, we were talking about LRC circuits and antennas and natural frequencies of circuits. And so in this case, we just want to figure out, this one's actually even simpler than that. The ideal size of an antenna is going to be 1/4 the wavelength size. And they're telling us that we're using an antenna that's 50 meters high, and we want to know what frequency it's going to broadcast at. Well, if the antenna is 1/4 the wavelength, and the antenna is 50 meters, then our wavelength is going to be 200 meters. And then we just calculate the frequency from 200 meter wavelength for a light wave, which is the speed of the wave, which is the speed of light in this case, divided by the wavelength, which is 200 meters. We get 1.5 times 10 to the 6 hertz, which is 1.5 megahertz, which is in the AM frequency here in North Platte. 1.5 megahertz is 1410 is ESPN radio. I don't know what 1500 is, but close enough. Anyway, then part B says to discuss the analogy, the fundamental resonant mode of an air column closed with one end resonance of pure antenna is 1/4 the wavelength. So in this case, they're talking about how in a tube of air you can have resonant frequency. You can have the base resonant frequency, which is the fundamental, and then you can have harmonics in certain tubes. And in this particular one, we want to know for an air column that's closed at one end, and in that particular situation, you had this equation where the harmonic frequencies were equal to n times the velocity of the wave over 4 times the length of the tube, but only for n equals 1, 3, 5, 7, 9, so on and so forth. So the reason that that's analogous is because one end of the antenna is tied to the circuit, the other end is open, the other end is just up there in the air. So essentially the one end that's tied to the circuit is going to be allowed to, or is going to be kind of tied down. The other one is going to be allowed to oscillate. So that's like the open end of the tube. The open end of the tube is always going to be at the frequency or at the air pressure of the air. The closed end is going to oscillate back and forth between high and low pressure. So that is problem 2. There's the solution for it. Problem 7 is the other one she wanted to do here. The lowest frequency in the FM radio band is 88 megahertz. What inductance is needed to produce this resonant frequency if it's connected to 2.5 picofarad capacitor? So this is a natural frequency or resonance frequency problem. And the equation for that in an LRC circuit is the natural frequency or resonant frequency f sub 0 is 1/2 pi times the square root of the inductance pi times the capacitance. And they've given us everything in this equation except for the capacitance. Sorry, except for the inductance. So we need to solve this equation for L, and when you do that, this is the equation you get. So to do this, you need to multiply both sides by the square root of LC to get the square root of LC over here. Square both sides, divide by C squared, and you'll get this equation here. Divide by C, rather, and you'll get this equation here. Then you just plug in your numbers, and you get 1.31 microhenries when you're done. And then in part B, it says the capacitor is variable to allow resonant frequency to be adjusted as high as 108 megahertz. What must the capacitance be at this frequency? So you're using the same equation, but this time you're going to solve for C with your frequency at 108 megahertz, and you get a 1.66 picofarad. So it's the same equation twice with different things that are known and solving for different things that are unknown. So that's problem 7. I've got to sneeze. Okay, next problem. The next problem is in chapter 25.9. Let's go see that. Chapter 25. Number 9. By how much do critical angles for the red and at 660 nanometers and violet at 410 nanometers light differ in a diamond surrounded by air? Remember the critical, excuse me. The critical angle is defined by a very simple equation, actually. It's the sine, the inverse sine of n2 over n1. And the critical angle is that angle at which you came into a surface, a surface boundary with a ray of light, and all of the light would go into the material, and the critical angle could be used in a lot of different. It could be used for total internal reflection. It could be used for entering material. It could be used for a lot of things. But anyway, that is that critical angle, and you solve Snell's law to get this. Anyway, you get theta. You get your critical angle theta sub c inverse sine of n2 over n1. For red, you're going from air, which is 1. That's the thing that's your n2, because you're inside the diamond, which has an n of 2.410. And so it turns out when you solve for the inverse sine of 1 over 2.410, you get 24.52 degrees. For violet, it's 24.01 degrees. Same, you get the same numbers, but you get different n's, because in air, the n for each of these colors is about the same, but in diamond, the n for these colors is different wavelengths. And that's something you can either look up or you can calculate. There is an equation for the change of a material's index of refraction by wavelength. I can't remember what it is exactly offhand, but it is there. It's in the book. The law of the diffraction, the index of refraction does change with the wavelength, which is why when you put white light through at a high angle, you get that splitting of the light, splitting of the colors. So that's that one. Let's look at 29.10. Chapter 29. Where's 29? There it is. .10. So in this one, we're doing an electron microscope. It's producing electrons that have a 2 picometer wavelength, and we want to know what's going to happen if these are going to go through. If these go through a 1 nanometer slit, single slit, what will the angle of the first diffraction maximum be found? This uses the same concepts as light going through any kind of light going through a single slit, and so we use the same equation: d times the sine of theta equals m times lambda. And where the d here is the width of the slit, the m is the order of the maximum or minimum. So if it's first diffraction minimum, then m is going to equal 1. And then your lambda is, of course, equal to the wavelength. And then the theta is the angle that we're going to solve for. So in the end, we solve for angle. We get theta equals inverse sine of m lambda over d, where the m is the order, so that's the 1 because it's the first diffraction. And then lambda is the 2 times 10 to the minus 12, the 2 picometers. And then you divide by the width of the slit, which is the large d there. And you get 0.115 degrees. It's just plugging numbers in. I think the hardest thing about these chapters really is just remembering what concept goes with which equation. There's no real, there's no real like multi-step problems in these last chapters. It's find the right equation and plug in the numbers. So very rarely do you have to do a lot of things, figure out the angles and calculate, the coordinates and calculate the different whatever. There's just very little of that going on in these chapters. So pretty Easy once you find the right equation. Just find it, solve it, plug it in. Okay, 29.10 we did, so 30.2 C. Rutherford, right? Remember Rutherford fired the alpha particles at the gold nuclei, at the gold foil, and he found the size of the nucleus in that experiment to be about 10 to the minus 15 meters, 10 femtometers. And this implied that there's a huge density inside the nucleus. And to find that density, we need to calculate the volume of the nucleus using that size. The size is going to be the diameter, so we need to take half of that, square it, multiply it by 4 times, multiply it by 4/3 times pi. So 4/3 pi r cubed, not square it, we need to cube it. So 4/3 pi r cubed will give us our density. And so that's what they do right here. Diameter divided by 2 is your radius cubed. 4/3 pi times r cubed gives you the volume, right? This is going to give you, this whole thing right here is going to give you about 0.5 times the diameter cubed in the end. And then to get the density, we need to take the mass of it, which the mass of gold is 197 atomic mass units, where 1 atomic mass unit is 1.66 times 10 to the minus 27. So you multiply that times 197, and you get this number right here. 3.27 times 10 to the minus 25 kilograms. Divide by the 0.5 times the d cubed, which ends up being 5 times 10 to the minus 46. And you get this density of 6.54 times 10 to the 20 kilograms per meter cubed. Holy crap. The density of the nucleus is insane. What's the density of the heaviest element on the periodic table? Density of the heaviest element on the periodic table, that is, I think, I don't really know exactly which one's the heaviest one. Let's see. One of these down here, it's probably, I don't know, could be a lot of things. Could be tungsten. That one's really dense. I don't remember if uranium is more dense or less dense than tungsten. It might be more. But some of these are really dense. Let's assume that it's uranium. The uranium density of uranium is something like twice that of lead. Let's find out. Density of uranium. It's 19.1 grams per centimeter cubed. Let's convert that. Density of uranium in kilograms per meter cubed. 18,900 kilograms per meter cubed. Okay, so that's 19,000. And what is this one? What is the density of the nucleus? Well, there's no name for that number, but it's a lot more, right? It's a lot more. 6 times 10 to the 20. So if you have like a liter of, let's go back here. So what's a liter? A liter is about this big. Take your hands, spread them out as big as you can, and make a cube on all sides. That's about a liter, okay? So if you have a liter of uranium, you're going to have about, what is that going to be? A centimeter cubed in a liter, there's 10 times 10. Is there really 1,000 in a liter? That's not right. Yeah, that's right. You're going to have 18 kilograms. So a block of uranium this big is 18 kilograms, which is going to be about 40 pounds. So a block half the size of this box is going to be 40 pounds. So that's heavy, very heavy. Do the same thing with, you do a liter of this stuff, and it's going to be more than the mass of our sun, more than the mass of the Earth in just this small little space. Okay? If you have more than the mass of the Earth in a space that small, it's going to be a black hole. Okay? It's going to have so much gravitational force in such a short distance, such a close distance to it, that it's going to suck in the light around it. That is some serious density. And that's exactly what black holes are. Black holes are neutrons. They're also called neutron stars before they become black holes. A neutron star is a star that is made completely of neutrons. It has no space. Neutrons do not repel each other. And so when neutrons get together and have a party, there's no space between them. They're all just sitting right on top of each other, right next to each other. They have no repulsive force, and so you get the most concentrated mass that you can possibly get in the universe. And it's a beast. One crowded party. All right, now we move on to 30.10. Oh, I must have looked at the wrong. No, I didn't. I looked at the wrong. There was no part C in that one, so I just did that one. Here's 30.10. What is the magnitude? Maybe she meant 3010C. No, we'll do all these again. Magnitude of the angular momentum for an L equals 1 electron. Calculate the magnitude of the angular spin angular momentum, and what is the ratio of these angular momentum. So this is quantum numbers, right? If little l equals 1 for an electron, then your angular momentum value is just given by this equation. Angular momentum is capital L. You just put in your L equals 1 into this equation, you're going to get 1 times 1 plus 1, which is, of course, 2, square root of 2. So you're going to get the square root of 2 times h over 2 pi. Right? If you calculate all that out, then you get 1.49 times 10 to the minus 34 joule seconds for the angular momentum. Plain and simple. And then they want to calculate the magnitude of the electron's spin angular momentum. Well, if you have little l equals 1, then little s can only equal, let's see, what I wanted to do is show you the charts for this really quick. Let's go to our book. Let's go back to the charts just so you remember where to find this stuff. Not this one. Chapter 30. We want to go to chapter 30.8. So here are all the quantum numbers and rules. These are the numbers that n can be. 1, 2, 3, 4, 5, so on and so forth. Then if n is equal to a particular number, then L can be any of the numbers below n, not including n, including 0. So if n can be 1, 2, 3, 4, 5, 6, 7, then L can be 0, 1, 2, 3, 4, 5, 6. Okay, those are all the possible L's you can have for that particular group of n's, for n equals 7. And then to calculate your angular momentum, you use that L in this equation. Then, once you've got L, then you also have the z component of the angular momentum that you can calculate here, and those quantum numbers can go anywhere from negative L to positive L in steps of 1. But then you also can calculate the spin angular momentum, which is the next one, right here. Spin angular momentum can only be 1/2 for electrons, so S has to equal 1/2. But there's also the z-axis angular momentum for the spin of the electron, m sub s. Don't get these two confused. The spin of an electron, s, is always 1/2. But you can calculate also the z-axis or the z component of angular momentum for the electron, and it can be either negative 1/2 or positive 1/2. So here's the chart that shows all the different options. We're calculating spin, which uses S, and it has to be 1/2 for electrons. And that's why in this thing there's nothing to really do except plug in 1/2 right here and then calculate. And that's where they get the 1/2 and the 3/2. You have 1/2 times 1/2 plus 1, which ends up being 1/2 times 3/2. Calculate it out, you get 9.13 times 10 to the minus 35 joule seconds. So this is the spin of an electron no matter what state it's in. It's always the spin of the electron. And then they want to know the ratio of the angular momentum of the overall angular momentum and the spin angular momentum. So they just take L over S and get 1.63 for problem 10. So those are Jennifer's questions. If anybody else has any questions, we can address them now.
On chapter 30, problem 3, I got close enough to get feedback to that one.
30, problem 3, Millikan's oil drop experiment. So this is the experiment where the oil is, there's a tiny little droplet of oil, and it's falling down in gravity, but we turn on an electric field to push it up again and to hold it still. So essentially the electric field force has to equal the gravitational force. So the first thing that we do is we calculate the electric field force, Q times E. The Q, of course, is going to be the thing that we're actually going to solve, I think, because they never tell us how much charge is. Yeah, we're going to find out how much charge is on the drop. So the Q is the thing we're going to solve for. The electric field, we do know what it is. The electric field is created by a voltage that is 2,033 volts with a separation of 2 centimeters. So you take the voltage divided by the distance between the plates will give you the electric field between the plates. So there's your voltage divided by distance. And so that's the value of your electric field. And then that has to equal the value of the gravitational force, which is mass times gravitational constant. And then you just solve this equation for Q. Now, some of the things that they do through here is they have to calculate, for example, the mass, because they know the density of the oil, but they don't know the mass of the droplet, but they do know the volume of the droplet because they know the diameter. So on this line, they're going to use the density equation, density equals mass divided by volume, to solve for the mass. They plug in the volume, 4/3 pi r cubed, and then they plug in the density, and they get the actual mass of that droplet of oil, and then they plug that mass into this equation. Once they plug that mass into this equation, then they can calculate the charge, which happens to be 2.22 times 10 to the minus 18 coulombs. Remember that the standard charge, or the quantized charge, is 1.6 times 10 to the minus 19. So that's not even that many charges. Right? And that's exactly how they figured out what the quantized charge of the electron was. Because they did this experiment over and over again, and they found out that every answer they got for the charge was a multiple of 1.6 times 10 to the minus 19. Every time. And they discovered that the electron always has the same amount of charge. Really, they discovered the electron is what we did. So, any other questions? Did that one make sense, or do you?
Yeah. If I had my notes, I would have looked back over them and compared that to see where I went wrong. Because I basically did most of that. I couldn't even imagine where I would have different.
Easy to get a little mistake in a problem like that, just a lot of little details. I am recording this, so make sure that you take advantage of that if you want to. It will be up on YouTube.
Problem 6, part B.
Same chapter.
Yeah.
So here we have an X-ray tube. Has an applied voltage of 100 kilovolts. We want to know what the most energetic X-ray photon it can produce, right? So essentially, your energy your electric field is the energy of the electron that you can accelerate is going to be equal to the charge of the electron, which is 1.6 times 10 to the minus 19, times the voltage of the electron. So you get 1 times 10 to the 5th electron volts for that most energetic photon it can produce. And then that energy can be plugged into the equation for the energy of a photon. The energy of a photon is Planck's constant times the speed of light divided by the wavelength. Well, energy is this number right here, 1 times 10 to the 5th. So solve this equation for the wavelength and plug in that energy right here. They actually converted it to joules right there. No, they converted it to joules right here. 1.6 times 10 to the minus 14 joules for 1 times 10 to the 5th electron volts. You essentially just multiply this times 1.6 times 10 to the minus 19 to get the number of joules. That's the conversion factor. Then you plug in your Planck's constant and your speed of light, and you get the wavelength of that photon. 1.24 times 10 to the minus 11 meters for that X-ray photon. Two equations, plug in the numbers, solve them. So remember that X-rays are produced by accelerated electrons. The energy of an accelerated electron depends on the voltage that it's accelerated through and the charge of the electron. And then that energy is also related to the wavelength through Planck's constant. Speed of light. Anything else?
Problem 7, part C.
Okay. Problem 7, part C. This one is energy level problem. So we want to verify the energy of the photon emitted when the neon goes from its metastable state to one immediately below, which is 1.96 electron volts. So here we have neon, which is jumping up to, let's see. So neon is the metastable state is this top one, and it drops back down to this state here that has this energy release of 1.96 electron volts. We want to verify that that photon is 1.96 electron volts. So how do you verify that? You verify that by taking the difference between the levels, right? So this jump is 20.66. This jump right here is going to be let's see, is that right? What do they tell us here? They're not telling us something here that we need to know. They should have told us what this energy is here to get this right. It may be in the book. Let's go take a look. I know that we had the neon. They talked about neon lasers in there, so maybe it is in there. I'm going to be in section 30.5 lasers would be. So we go in here and look at lasers. Here you go. Here it is. I guess they don't give us that information, but they should. Well, that is kind of a bad question, I suppose. Well, it's a good question, just has bad information in it. They should tell you this other transition, but they don't. Neither in the book nor in the. Let's see, maybe they do here. Figure shows. No, they don't tell us.
What confused me about it was that they basically gave you the metastable state that they were asking for. And
Yeah,
I put in the other transition to 18.7, like it for the answer the first couple times, so I was confused.
yeah, that is. They should have given us the 18.7 for us to calculate the 1.96. They should have given us this. So that's just bad information for this question. I will remove that question from the homework so that you don't get docked for it. What number was that?
It's problem 7, chapter 3.
Problem 7. All right. Any other questions? What other problems do we want to do to prepare for the final?
Can we go to chapter 28?
28? Sure. All right.
Problem 5, part A.
Problem 5. A galaxy is moving away from the Earth, speed of 1,000 kilometers per second. So this one's going to be a relativistic problem involving the Doppler effect, right? So relativistic Doppler effect says the wavelength that the observer sees is equal to the wavelength of the object times this kind of lambda factor. It kind of looks like the lambda factor, but it's not exactly it. 1 plus u over c, 1 minus u over c, where u is the speed of the object that's emitting the light, and c is, of course, the speed of light. So the u, in this case, is how fast 1,000 kilometers per second, which is 1,000,000 meters per second. So it's 10 to the 6 meters per second. In both cases there. You just plug those two in there. The wavelength it's emitting is 656 nanometers rather, and we just calculate 658 nanometers. So there is definitely a redshift. It is a slightly longer wavelength than it should be, by 2 nanometers. Then the radiation is visible red light, because it's 658 nanometers. That is red. And then the last thing is why is the speed of the Earth in its orbit negligible here? Well, you could include the speed of the Earth in this, but the speed of the Earth is so much slower than 1,000,000 meters per second. So in this case, we're calculating the speed of the Earth is 2.97 times 10 to the 4 meters per second. That's 100 times less quick than the galaxy that's moving away from us. So it's just not going that fast. 1,000,000 meters per second, that's starting to be relativistic. Earth's movement is not relativistic. So it doesn't really matter. Doesn't take it's a 10 to the 5th factor. It will only show up 10 to the minus 5th factor. It would only show up in that 5th decimal place out there. It just wouldn't make a big difference. So again, it's just you got to know the right equation to plug numbers into. And plug it in.
That one, I was the whole relativity chapter. I was really struggling to read for some reason. Every time it came up, it was some kind of
Relativity is hard for a lot of people, mostly because we have no intuition for it. We just have to take Einstein's word for it, right? We don't observe relativistic effects in our lives. So why would we grasp it easily. We don't. It really takes, you have to really kind of separate your mind from your reality and think, everything that I think I know is not real. Okay, you have to kind of think that way. You have to think we're going to live outside of our reality for this. So, it's kind of hard, but probably the easiest way to do it is to just believe what the book says without trying to understand it. Just believe it. And eventually, you'll start, the belief will turn into a little bit more understanding in time. I guarantee you, the first time I studied relativity, I just had to believe it. And I had to do an oral exam on it with my professor, one-on-one. He gave me all kinds of scenarios to do. Like, can you make it to Alpha Centauri in your lifetime if you can go all the way up to the speed of light, but not actually the speed of light? I'm like, oh crap. Can I? And I just kind of guessed. I'm like, sure. And I was right.
Oh, good.
Because I figured, if you can go all the way up to the speed of light, then you can pretty much get there any time that's greater than no time. So you can get there in a second or a point second or whatever. But anyway, doesn't matter. It's just believing the math. You got to believe the math. So. Any other questions from anybody? Number 11 in the same chapter.
Oh yeah. That was probably.
Beta decay. So beta decay is a type of nuclear decay where you've got a neutron inside of a nucleus that's not happy, or just a nucleus that's not happy. And as this nucleus tries to rearrange itself to make itself happy, one of the things that happens is that a neutron decays and becomes a proton, an electron, and a neutrino. It goes through a process that creates a proton, electron, and neutrino, and some energy, and the neutron disappears. And so the proton stays inside the nucleus, turns that nucleus into something else, jumps it up one step in the periodic table. The electron and the neutrino are kicked out with the energy that's left over at high speeds. And the beta particle is that electron. And it can come out at really high speeds. So if it's given 0.750 mega electron volts of kinetic energy, what is its velocity? Well, mega electron volts, you can be pretty guaranteed that an electron with mega electron volts is going to come out at relativistic speeds. So you got to use the relativistic equation for kinetic energy, which is not a simple equation. It's not 1/2 mv squared. It is gamma minus 1 parentheses times mc squared. Okay, so the gamma thing is the problem here. It's a pain in the butt. The gamma is 1 over 1 minus v squared over c squared. V squared is the thing that you're solving for. So we're solving for this really messy thing. But that's okay. We'll first calculate. We will first solve this for gamma, and then we'll calculate v after that. So if we solve this equation for gamma, we're going to get kinetic energy plus mc squared over mc squared. And the kinetic energy is given. It's a number. It's 0.750 mega electron volts. We make that conversion. Here's the conversion factor into joules. And then we add that to our mc squared, the mass of the electron, times speed of light squared. Divide by the mass of the electron times speed of light squared. We get the number 2.4636. That is our gamma factor. The gamma factor of 2.4636 is definitely relativistic. Anything really above like 1.1 is relativistic. So 2.4 is definitely relativistic. Then we plug that number into the equation for gamma. The equation for gamma is gamma equals 1 minus v squared over c squared square root 1/2. Right? Sorry, taking the 1/2, which is the square root. 1 over, which is negative 1/2. But anyway, the point is that if we solve this equation, we can get it done. We're solving this equation for v. We're going to take both sides of this equation to the 1/2 power. This one's going to go away. This one's going to be to the 1/2. Sorry, that's not what we want to do. We want to take both of these to the negative squared power is what we want to do. We want to negative square both of these. I hate that they do this -1/2 thing because it really confuses the heck out of people. But if you multiply, if you take both of these sides to the -1/2 power, this becomes 1 over gamma squared, and this just becomes 1 minus v squared over c squared. Anyway, then we solve that for v by doing this. We're going to take a square root of both sides, where the c will just be c squared will just become c, and we'll get 1 minus 1 over gamma squared to the 1/2 power. And then you just plug in your gamma, and you get 0.914 times c. You don't need to plug in c because we want to know this as a fraction of the speed of light. So we're going 91.4 times the percent of the speed of light. 91.4% of the speed of light in this case, definitely relativistic. Definitely. Which is why beta decay is dangerous. Electrons are flying around all the time. There's always electrons bouncing off of us, going into us. Actually, electrons usually penetrate a little bit. But electrons that are at 0.914 C, they really penetrate and they really do damage in the skin. As they get into your skin, they can break apart things like DNA and stuff like that. So beta decay can be dangerous. Not the worst dangerous thing out there. It's not the worst kind of radiation, but it can be dangerous at high energies. Oh, right. Oh, part B2, right? Comment on how the high velocity is consistent with the kinetic energy it compares to the rest mass energy of the electron. So the rest mass energy of the electron, you can calculate it or look it up either way. The rest mass energy is always mc squared. So E equals mc squared is the calculation for rest mass. You take the mass of the electron times c squared and you get 0.511 mega electron volts. Kinetic energy is 150% of the rest mass energy. And when you've got a when you have a kinetic energy that is much more than, or more at all, really, than the rest energy, you're definitely in that realm of thought traveling close to the speed of light. You're definitely relativistic. So, any other questions from any other chapters, exams, or whatever else?
We looked at a problem 7 on that same chapter.
Velocity of a proton with a momentum of 4 points. So again, we're talking about momentum in the relativistic sense. It's pretty much in this chapter. You're just going to use all the equations from this chapter and not think about the equations outside this chapter. So relativistic momentum is gamma times m times u, where u is the velocity again. And in this case, they've given us the momentum, so we're going to solve for u. So we solve this equation for u, but the problem is u shows up twice. It shows up in the gamma, and it shows up here, m times u. So that's a little bit of a challenge. If you don't remember how to do that, let's do it really quick. Let's do it on education so everybody can see it. So P equals gamma, wish I could do this on my iPad, it's so much easier. Gamma mu, right? But gamma is equal to 1 square root of 1 over 1 minus u squared over c squared. So u is showing up in two places, so it's this thing times m times u, right? Now, the way that they do it in the book is they make it a little bit easier. They take the square root of the 1 on the top so that you can erase that. Then you can put your m and u up here. Just makes it a little cleaner. But it's the same thing. So this is the equation, but we already know the momentum, so we need to solve this equation for u. Right now it's solved for p. So I'm going to start by getting rid of the stuff that's in the denominator down here. This is a refraction, remember. This stuff in the denominator, I'm going to multiply both sides by this square root. So I'm going to get m times u on the left side left over. And I'm going to get p times the square root of 1 minus u squared over c squared. All right. Then I'm going to square everything to get rid of. Actually, I'm going to I'm going to square everything to get rid of the square root. So everything on both sides, m squared, u squared on this side equals p squared, squaring everything. And then when I square the square root, I'm just left with 1 minus u squared over c squared. Right? Terrible mouse writing skills. So now I need to solve for u. So I need to get all the u's on one side. The first thing I'm going to do is I'm going to divide by m squared really quick on both sides. We'll get rid of it here, right? So then I've just got this thing. So I'm going to put all the put this p squared over m squared into this polynomial here, and I'm going to be p squared over m squared c squared times u squared here. Right? Equals u squared. Now, many of you will be tempted to take the square root of everything right now. Don't do that. You will be screwed if you do. It's not correct. You cannot take the square root of individual things that are separated by pluses and minuses. That's illegal. So what we really need to do is add this thing to both sides. Add p squared, u squared, m squared, c squared to both sides. It will eliminate it on the right hand side, and on the right and the left hand side we'll get u squared plus p squared u squared over m squared c squared equals p squared over m squared. All right? And then we're going to factor out the u squared on the left-hand side. Oops. Come on. Come back to me. We're going to factor out the u squared on this side, so we're going to get u squared times 1 plus p squared over m squared plus, or m squared c squared. Equals p squared over m squared. And then I'm going to divide both sides by this polynomial here. I'm going to get u squared equals p squared over m squared divided by 1 plus p squared over m squared c squared. Then I take the square root of both sides. On the left side I'm going to get just u when I take the square root. On the right side I'm going to get p over m, taking the square root of the top, and then taking the square root of the bottom, I'm just going to get the square root of 1 plus p squared over m squared c squared. Can't take the square root of those things separately. So you got to just take it all at once and call it good. And there you go. And that's what we get when we come back here. That's what this is right here. Right here. They did it slightly differently, but it all comes out the same way. In the end, you get, let's see, they're missing something here. They actually did this wrong. I think they did it wrong anyway. They should have divided by m squared here. Oh, they actually just put the m into this thing first. And that works too, I suppose. It works either way. It's the same either way. So anyway, once you've got that, you can just plug in everything that they've given you. Because they've told us the momentum, that's the P, and we know the mass because it's a proton, and we know C because that's the speed of light. You just plug in those numbers and you're good to go. 2.0 times 10 to the 8 meters per second is what they get. So getting very close to the speed of light there. 0.67-ish speed of light. Any other questions? Anybody else have any questions? Are we done?
I think I've got something here on chapter 30.
Do we have a chapter 31?
Yes.
We do.
In problem 6, that one was,
The activity of carbon-14 in 1 gram of carbon-12 found in living tissue is 0.250 becquerels. So, the activity of carbon-14 see, it's 0.250 becquerels. So we have to go back to our book for this one. To get the numbers out of the book. Activity and rate of decay right here. This is where we're going to do this. So becquerels is the rate of decay, or what we call the activity, and it's calculated in a couple of different ways. You can calculate it from the change in decays, so the number of decays that occur over the change in time that it happens. But you can also calculate it using its half-life. So if you know the half-life of the material, then you can take 0.693 times the number of nuclei, how many of the radioactive things you have, divided by the decay rate. So we know the decay rate, well, not the decay rate, but by the half-life. We know the half-life of carbon is 5,730 years. That's in the book here. So this is the equation we're going to use to calculate this in the homework. And you can see that they're doing that here. The rate is going to be 0.693 over the half-life. The half-life is 5,730 years. But they do have to convert that into seconds because seconds is the SI unit. So they convert that because 3.156 times 10 to the 7 seconds per year will give you seconds. So I get the seconds down here. So the only thing we really need to know is how many radioactive nuclei we have. Here it says we have, it's in 1 gram of carbon-12. Well, then we need to know a percentage, the percentage of carbon-14 that is in living tissue. And that we find carbon-14 what did you say?
I think we projected that.
Oh, I can't do anything about that. It's just going to have to come alive on its own again here. But previously in the chapter, it tells us that carbon-14. See if I can find it. The percentage of carbon-14 in living tissue is. I can't find it. I can't find it. I'm going to look it up. In the book first. Carbon-14 half-life and activity, which is where we're at. Does it show up anywhere else? Um, no, I can't find it in the. Wait, here we go. No, that's not either. So here they show it as by 6. Here they show it as 6.02 times 10 to the 23 over in 12 grams. So in 12 grams of it, there's going to be 6.0 times 10 to the 23 particles of atoms of carbon-14. I don't know where they get the number. You could look it up. I couldn't find it in the book, but it is in the book somewhere. But you could also just look it up on Google. But what you're looking for, what this number is the number of, it's the number of, it's the number of carbon-14 atoms in living tissue before it dies that are carbon-14 atoms. You can either find it in the book or look it up on Google, but that's the number they need. So you end up with that ratio, and then you multiply by the mass, and you get that number 6.52 times 10 to the 10. And then you just plug it into the equation for the rate, and you're done for that. So it's on the video, even if it's not on the screen. I'm going to turn this. Well, it already turned itself off, apparently. Turn it back on again. See if it comes back on.
And, I think I've only got one more thing to number 9.
Same assignment? The decay equation for uranium-235. So the decay of uranium-235 is alpha decay. And you can look that up in the book. It's in there in several places. You could also look it up on the table of nuclides, and it shows it there as an alpha decay. When alpha decay occurs, what happens? What does the nucleus lose when there's alpha decay? Nope. It does lose 2 protons, but not just that. It loses a helium nucleus. 2 protons, 2 neutrons all grouped together. Right? That's what alpha particle is. So it's going to lose 2. It's going to lose 4 total things from its nucleus, which means it's going to go from 235 to 231. And it's going to lose 2 protons, which is going to be 92 to 90. So it's going to become thallium. Thallium or thorium? I think it's thorium, not thallium. Thorium. So 235 becomes thorium and releases the alpha particle. So this is just what happens normally with, this just happens spontaneously with uranium. If there's enough uranium really packed close together, then this alpha particle could actually cause, well, and there's another thing that happens with these things too, is the fission. So you get this kind of decay happens, but also fission can happen if you have enough of them together. Close together, that fission can cause a chain reaction. So, and they want to know in part B what energy is released in this decay. Well, you calculate the masses of these particles. The masses you can calculate from the periodic table. The mass is this number right here underneath it. That's the mass per mole. Right? So you take those masses and plug them in per mole here, and that's what they're doing right here. The mass of, in part B, you get energy equals the change in mass over c squared. So the change in mass is the mass of this guy. That's the 235 minus the mass of this guy plus the mass of this guy. So you might subtract over those two masses, multiply by the speed of light. The speed of light squared has a value in this chapter of 931.5 mega electron volts per c squared. And I would use that one per unit also. I would use this for the speed of light squared instead of c squared, because that will give you a number that you won't have to do as much math. But you end up with 4.679 mega electron volts for the energy that is released during this decay. Assuming the residual nucleus is formed in its ground state, so assuming that this is not an excited atom in any way, what is going to be, how much energy is going to go to the alpha particle? Well, if this thing is in its ground state, then all of the energy will go into it. So how much energy goes? No, I'm sorry. Not all of it, half of it. So the energy it's not going to be about energy, it's going to be about momentum. That's what's going to happen, because momentum is going to be conserved. So the momentum of the alpha particle, the momentum of the thorium. I don't say it wrong. No, it's thorium. The momentum of the thorium particle, the momentum of the helium particle will be the same in the end. And so you can calculate those as equal coming from the energy release. So I don't know if they actually do the calculation here. Yeah, they do. Here we go. So here's the energy. Here are the two energies of those two particles and the two momentums of those two particles. So you have two equations, two unknowns, and you solve them. Essentially, it's just a classical equation here. This is really and so what you can do is, since the momentums have to be equal, you solve the momentum equation first for the velocity, and then you plug that into the energy equation, and you get this equation, which gets a little bit messy. But in the end, you're just plugging in the energies and the masses, the total energy and the two masses to calculate the energy of the output. So that's it.
That's a big, messy problem.
It's a mess when you start plugging these two into each other, but it's the same exact process of doing a conservation momentum equation that we did in the first semester. We've done this, we did this probably 50 times last semester, easily. Where your conservation, where your momentum is conserved, but your energy is not. That's the same. And so you solve the momentum equation. This is the what did they call it? A collision that's perfectly inelastic or something like that. Yeah. A perfectly inelastic equation. This is the same kind of solution, except in reverse. Starts as one mass, becomes two masses. So it's the same process, just backwards from what we did last semester. I'm sorry? YouTube. Go to search YouTube for my handle, which is MPCC Engineer. And doesn't, no, I don't like, and then it tells you it's searching for a different thing. Go back to what you were searching for, and it'll take you to my channel, which is this guy right here. So this is my channel, and then you can look at my playlists, and go to Physics 1420 Spring 2017. And they'll all these videos are here. Now we're recording in class. And it'll be the last one on the list. So this one was, is this Tuesdays? Maybe not Tuesdays, but last Tuesday maybe. So that MPCC Engineer is my YouTube handle.
And this one here will be uploaded.
This one will be uploaded as soon as class is over. That is correct. Anything else? Number 6, was that the one we were just looking at? That one? Do you have a question about it in particular, or just want to look at it again? Final exam is up and available, I believe. Should be an expert TA. So you can make your appointment whenever you're ready.
On chapter 30, we take a look at problem 11 real quick. That one.
Are you done with this one? Almost. Matt, did you hear about the talk next Tuesday?
Yeah.
Oh, it's actually talking to Matt Martin. You guys, 2 Matts at the same table. So if you're interested, just tell me before Monday so I can hold a lunch for you, because it should be a really cool presentation. I don't know if you have a final or whatever that day, but so far I still have at least 5 spots left over. So. The questions? Yeah. Let's finish up here and then I'll get that. You good? Okay. So chapter 30, what?
Chapter 30, problem
11? Spectroscopic notations are allowed. Which ones are allowed? Which violate none of the rules regarding the values of quantum numbers, right? So remember, the rules for quantum numbers come up in that table we were looking at here in chapter 30. Chapter 30. What is going on? Oh, I need to stop that. There we go. Better. All right. So going down to chapter 30, and we go to quantum numbers and rules. And we have all these different quantum numbers, right? L and S and N and whatever else. And then we have this table of rules here, right here. These are the rules that are the numbers that are allowed in specific situations. But then also we have the shells and subshells thing. And this one, remember I told we were talking about this as the old, kind of old-fashioned one with the old-fashioned one from Germany, from Europe, where you have the n number is the first number. It's the first shell, so it's the shell, and you have 1, 2, 3, 4, 5, and so on and so forth. We're just going to go from 1 to 5, and then the subshells being the L number, and then you also have a symbol that goes along with it over here. And so if you're in the first shell and the L subshell, then you have a little s that's representing what you're doing. And if you're in the second one and the first subshell, you're in a P. Then if third and the second, then a D, right? And so that's what they're using here is that system. So for example, the first one, are we doing 11? Is that right?
Yep.
So 11 is 1s1. What is 1s1? Well, let's go back to our thing here. 1, it's n here. S is in L equals 0, right? And then you have the 1 at the end, which tells you how many electrons are in there. So 1s1 would be n equals 1, L equals 0 for S, right? S, when it's S, it means L equals 0. That's allowed because when n equals 1, L can only equal 0. That's your only option. But there's only one electron in the shell. Is that allowed? Yes, it is. You can also look at it in terms of the periodic table. 1 corresponds to the shell that is normally occupied in this first row. And the S means that you have one pair of electrons because it's anal number 0. And then you have one electron in there. Can that exist? Is there one thing up there? It's this one. And then if you had 2 S1, then you also have enough to do that. But you can also have 2 2 P, because you have extras. But anyway, it's just kind of how that works. So you have to just see if it's breaking any of the rules. The first number is the N number, the second one is the L number, and the third one is the number of electrons that are kicking around in that shell, right? The number of electrons that you can fit in this shell are 2. 1, 2. This one you can fit up to 8. Okay? This one you can fit up to 8. This one you can fit up to 20 or whatever it is. I don't know how many it is exactly, but it's a lot. But anyway. So that's kind of how it goes. So let's take a look at, so in the subshell 2s, you can fit in 2. This is another one they're showing. In the subshell 2p, you can fit in 6. So you can have a 2s, 2p state that is 2p, 2s2 and 2p4, or 2s2, 2p6. But you can't have any more than that. Okay? Because in the p states, you can fit in as many as 6 for a total of 8. In the S states, you can fit in 2 for a total of 8 combined, right? So how do we decide what is allowed and what isn't allowed? Well, it really all comes down to what you've got in the letters. For S states, you can fit in a total of 2. For P states, you can fit in a total of 6. For D states, you can fit in, I don't remember how many. Also 8, I think. Yeah. Also 8 in the D states. But it's 8 more. So if you're in the D state already, then you've already got P states underneath it. So anyway, here is the table that's really going to help you, because it's going to show you what are the ground state configurations, and anything less than that you can put in. So the ground state of sulfur, for example, has all these things: 1s2, 2s2, 2p6 is the filling of that one, and then all the way out here to 3s2 and 3p4. So S's can only have a maximum of 2, and L's, P's, and D's can only have 6 each, for a total of 8 in each level. And again, it comes down to here. Comes down to kind of counting on the periodic table. But let's take a look at that actual problem and see what we've got there. So, was it 11 we're doing? That's right. So 1s1 is allowed because S can have 2 in it, and we're in the first state. 1d3, can that one be in there? Why not?
The D is impossible to make.
That's right, n equals 1. If we go back to our chart here, let's see, where is it? If n equals 1, the only possible L state is 0 with an S, right? When n equals 2, you can have an L equals 1, right? And then you can have a P state, but for this one you can't. And a better showing of that is actually this one. So this is the only 1s1 state. These are the only two 1s1 states allowed, or the 1s states allowed. 1s1 and 1s2. If you're gonna, you can like lithium has a 1s2 state, but the last shell is actually the 2s state. This is the inner shell. This is the valence shell out here. So these inner shells they're there, but they're not the valence shell. So the thing you want to look at is the valence shell. And that's what they're showing us in. So 1D does not exist.
And quick question about that 2s1. Since S begins with the previous state, the 2 is 2 allows for S also, right? Since
Yeah, every single n state has an S state because S is L equals 0, right? That's why I like to look at periodic tables because it kind of helps us to keep track of it. If we're just talking about ground state atoms, then the 1s1 ground state atom is hydrogen. 1 is the row. S is, there's 2 electrons, right? And then 1 says that we're talking about the first row. 1s2 would be the first row. There's 2 electrons because it's an S configuration. And the second one would be helium. Now in the second row, we have a 1s1 and a 1s2 as well. Okay? We have a 1s1 and a 1s2. But we also have a 1s1, a 1s2 P1, P2, P3, P4, P5, P6. Okay? Ground states. So 1s2, 2s1 is lithium. Right? 1s1 takes care of those 2 electrons. 2s2 takes care of that one, or 2s1 takes care of that one. 1s2, 2s1, there we go. And then beryllium, which is the next one, has the 1s1 electrons, which also helium and hydrogen have, but it also has 2s1 and 2s2. That's beryllium. So 1s2, 2s2 takes you to beryllium, right? 1s1, 1s2 gives you those 2s2, and 2p1 gets you to boron. And you're just counting along there. Sorry, 2p1 gets you to boron. And then 2p2 gets you to carbon, and so on and so forth. Until you fill up that shell all the way to the end of that row to 2p6. And then sodium. You get 1s2, right? 2s2, 2p6, right? All the way to neon. And then sodium would be what? 3, third row, S1, right? And so for sodium, you get 1s2, 2s2, 2p6, 3s1, right? So in the periodic table, the S's are here, and helium gets put over there too, right? So you get the S's plus helium in the S's. Those are all S's. These are all P's. These end up being your D's. And then you just count for the ground state. Okay? Now it turns out that any atom that is at a particular place can reach into different levels, can be at different levels. But we're only just talking about ground states. So calcium, for example, where's calcium? I always forget what calcium is. Here it is. Here's calcium. Calcium is at 1s1, I'm sorry, 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2, right? But it can lose an electron and be at 4s1 also, it turns out. It can also, its valence electrons can be jumped into different states. Its valence electron here can, well, it's a full state, but it can actually, so if it loses an electron, if it gains an electron, which is actually more likely, so the most likely thing for calcium to do is to gain electrons when it becomes an ion. So when it gains an electron, it can be in the 2p1, right, a 4p1, or 4p2, or even higher. It can jump up into different states. So those can be in all kinds of different configurations. And it can gain 2 electrons. You can get a dimer ion, which is a 2 plus ion. So the ground state for the 2 plus ion is actually 4p2 up here, but those 2 electrons can occupy any of the states up here that would normally be ground states for other atoms. So you can jump it up, you can ionize it and jump it up into different states. And that's why they use this, because it corresponds with the periodic table. Is that starting to make sense a little bit? So you have your S's, you have your P's, you have your D's, and then you have one more. This row down here is one more, which is what's the last one we use? Is it H? Can't remember. PD, no, it's F. SPDF is the next one. And then they even have more after that they can jump into more energy levels. So, because this only goes so far to help you to understand that. Because the energy levels are more than the periodic table. But anyway, it's just helpful for me, I think, that way. So, let's see, where were we? Problem 11, right? So, the only ones that are allowed are that first one, 1s1. Second one not allowed because if n equals 1, you cannot have an L equals 2 or 3. D is 3, right? So you can't have an L equals 3 if you have n equals 1. If you have n equals 4, you can have a 4s2, right? 4s2, that's calcium. We're just talking about that, right? You can have 4s2, that's perfectly viable. So C is allowed. And then D, 3p7 is n equals 3. What's P? No? P is 3, right? Can't have it. If n equals 3, 1, 2, 3, you have 3, oh yeah, P is allowed. But what's not allowed? How many electrons can you have in the P state here? 6. How many do we have?
7.
7, not allowed, right? What's the next one? 3P, E6H20. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Can you have it? 20, right? 6H20. Well, H20 takes us all the way down to this guy. And there are 20 spaces. There's plenty of room out there for electrons. And you can have that H level out there for sure. So that one's allowed. So the periodic table can help you a little bit. It's help you to visualize it. It's not going to take you everywhere as far as understanding all of that, but all they're really doing is showing this way of mapping it out shows you how many electrons can be in each state and what their quantum numbers are in kind of a shorthand. When they just show you like 4s squared, they're showing you just the valence shell, just the outside shell of electrons, assuming that all the other shells underneath are full to capacity. So in this case, they're just showing you the last two electrons for calcium, if it's in the valence state. But 4s2 could also be something else that's not in its ground state. It could be an excited state. Okay. Any more questions? Are we done? Yeah, we took almost the whole time. We took more than the whole time. All right. So, exam is open and ready to go. I can be available. I can be here today for a couple more hours. If you guys have any makeup or work you want to do. I can be here tomorrow morning. I'll be here tomorrow morning, all morning, until probably noon or 1 o'clock. So,
Bring in the lab assignment.
absolutely.
Thank you for
Yep.
Do I need to email you what time I want to schedule that exam or?
Nope. If you just schedule an exam at the Success Center, should be fine. In fact, I'll go over to the Success Center right now and give them the password and everything so before I forget.